All right, so let's go ahead and take a look at this next idea. So we're going to look at what happens with r prime of t. I'll remind you of one formula that I have right here, this one right here actually, that r prime of t is going to be, and I can multiply here by t prime, or t only, not t prime, times r, the magnitude of r prime. So I'm going to just multiply this equation on both sides by the magnitude of r prime. Would have been much easier to say that. Oh well, that's what I'm doing. All right, so with that and this formula here, I'm going to have that the r prime is going to be t times ds dt. And yes, this calculation is a little bit annoying, but we'll get through it. It's not too bad though. So let's go ahead and take the second derivative here of r. I'm going to start dropping the parentheses t to make it more compact. So the derivative here, you have to do a product rule because there's a product. So you're going to have to do t. And by the way, this is a scalar, but you still have to follow your product rule, because you would have to basically put each the ds dt into each one of the components, and then you would do a product rule in each component and split it out. So you still have to do it. You don't get away from the product rule. Anyway, so derivative of the first times the second plus copy the first times derivative of the second. Okay, and now we're going to do something that, if you don't know what the result is, it makes absolutely no sense, but this is just basically what we need to make things work. So I'm going to do r prime cross r double prime, the cross product. By the way, at this point, this only works for 3 dimensions. At this point, you cannot do this for 2 dimensions, because obviously the cross product only available for you for 3 dimensions. So at this point, I abandoned my 2-dimensional case, and this formula is only for 3. I forgot to say it, but here, once we do the cross product, it's pretty obvious that we have to do that. Now, r prime, remember, I wrote as, right here, t ds dt. So I get t ds dt cross this thing right here, and I forgot to write my cross. I said it, but I didn't. So I'll put it here just to not erase this here, t prime ds dt plus t d2s dt squared. Now, this right here, you have to remember that the cross product is going to be distributive, or linear in that sense. And so you can move this in, move the scalars out. So you're going to have t cross t prime times ds times ds. Sorry, ds dt times ds dt, ds dt squared. Now, when you multiply this one, who cares what that is? Well, we should care. But you have ds dt. But why am I saying that is because, well, this thing right here is 0. When you do a vector times across itself, you get 0, so that whole term goes away. So I just get this here, t cross t prime, and then ds dt squared. Now, I'm going to remind you of one fact that we talked about, and that is the fact that t and t prime are orthogonal. They're perpendicular, meaning then that if I want to calculate the magnitude of t cross t prime, I use my formula that I said we hardly ever use, but today is the day where we use it. I said that in the previous video. I said, why? Because you already have one with a cosine. Why would you even bother? But this formula will be rather useful, because here you'd have to have the sine of the angle between the 2 vectors, but then t and t prime are orthogonal, so this just becomes sine of pi over 2, from where we get the magnitude of t times the magnitude of t prime. But t is a unit vector, so that's just 1. So when I do the magnitude of this, I just get the magnitude of t prime. Now, what we have to do then is if we take magnitudes here, we're going to obtain that this is going to be the magnitude of this times ds dt squared. And that is going to then be the magnitude of t prime, which is going to be, where did I leave that one? Oh, no. The magnitude of t prime, I need that one actually. So let's go ahead and try to put things together. Where? Here. The magnitude of t prime, I need it right here. That will be substituted in by t cross t prime. I almost got lost in my whole calculation. Thank goodness I didn't. So the magnitude of t prime equals to this. I plug it into here. And then I have to divide by r prime of t. And you say, well, you made it more complicated, but not yet, because that product t cross t prime, I can substitute in with r prime cross r divided by this guy right here. But ds dt, remember, is just r prime. So when I plug everything in, it's just going to give me r prime cross r double prime over magnitude of r prime. I had 1. I'm going to get 2 from here. When I divide, I get 3. Whew, that took us a minute. But this formula right here is the one you want. It took work, but we have it now. Why? Because if I give you a function, now to compute the curvature, all you have to do, a vector value function in 3 dimensions, by the way. For 2 dimensions, you still are going to use this one. There's no way around it. But in 3 dimensions, you have this formula that's even nicer. Why? Because now you take your derivative, take second derivative, and then divide by the magnitude of the, do the cross product and divide by the magnitude of the derivative squared. Why is that better? Well, because to compute this one, remember, I have to do the derivative of of t, which is already a fraction. So it's going to be, I'm going to have to do here a quotient rule, take a magnitude, then a magnitude of this. The formulas for this, when you express them like this, in this form, get really, really messy. So if you can do it with this formula, it's much better. All right. Wow, that was a lot to go through. So let's go ahead and write all the formulas. We're going to do one consequence of this formula here. And after that, we're going to do a small example, and we're going to wrap the video up right there. All right, so let me erase here this whole proof, and I'm going to write a nice list for you. I'll be right back. All right, so we're going to talk about one special case. So let's say that you have a 2-dimensional curve where y is given. So the curve is given in terms of a function of x. So back to Calc 1. So let's say that you can do that. The question is, can you compute the curvature in any reasonable way? And what we're going to do is we're going to grab our function. We're going to parameterize it by this. I want to put it into a, so what we're doing is we're having our xy plane. We're laying it down here. And we're just setting our z equals to 0. And so we have a curve that goes around here, and I got to be careful to make it be a function of x. So it has to be, now it's not the vertical line tested, it's a line in this direction, can only hit 1. But I'm restricting everything to a, oops, not very well drawn, but to the xy plane. And so any point here is going to be of the form x, and then f of x for the y, and then 0 for the z. So I'm using that. So embedded a 2-dimensional curve into my 3-dimensional space, and I will go ahead and use this. So r prime is going to be just, my parameter is now x, right? Instead of being t. Well, fine. So r prime of x, if you will, looks ugly, but whatever, it's going to be this. Derivative is going to be 1. This is going to be f prime. And this is going to be 0, because derivative of 0 is still 0. R double prime, very easy, 0. F double prime, 0. And I'm going to go ahead and compute the magnitude of the cross product. So I got to do my ijk. I want to put in the right order. Oh, I have almost no room. I'm going to just write f prime, abusing notation there a little bit, but I just didn't realize I made my matrix too small. Nonetheless, it's still going to be the same cross product. So I'm going to copy my first column and copy the second column. This was f double prime. And I want to compute my cross product here. In the diagonals, I get 0 when I hit this one, 0 when I hit this one. This one survives, so it's going to be in the k coordinate. I want to have f double prime of x k. So far, that's the only thing I have. And now on the way back, let's see if we hit anything that is non-zero. And I believe we don't, but let's check. No, 0, 0. Everything has 0. So that's that. That's our cross product. Okay, so we can plug that in there. And then the magnitude of r prime we can compute right here directly. And so we can just put the curvature. I believe we can fit it here. This is k, not kappa. So kappa obviously looks different. Normally doesn't, but today it will. So that's going to be the magnitude of the vector here, which is going to be just the square root of the sum of the squares. Well, that's just going to be the absolute value of f double prime of x, and then divided by the magnitude of this vector right here, which is the square root of the sum of the squares, which is 1 plus f prime of x squared. So your curvature can be computed rather easily in the two-dimensional case, even though I was telling you, oh, for 2 dimensions, I have to do this one for sure. But you got to be, the only caveat is here, I was able to write the function as y equals f of x. Now, if you have a curve that cannot be written in that form, you go back to this one again. All right, so let's go ahead and compute one example, and I think that's where we're going to wrap up the video. Let me copy that one there. So I'll be right back. All right, so let's go ahead and at this one. We have 1 in 3 dimensions, so I hope that you, after the effort we put into this formula, I hope that you want to use that one. So you're going to compute r prime and r double prime. So r prime is going to be 1, 2t, 3t squared. Almost forgot my square. Oof, embarrassing. Double prime is going to be 0, 2, and then 60. By the way, my example is probably the hardest one, right? But I mean, the mechanics are the same. Of course, you're going to get more complicated functions, but the idea is the same. So you're going to then do your cross, for which you need your ijk's. And you're going to put first r prime, and then your double prime. And you're going to augment and do your determinant, unless you really want to do like a cofactor expansion. But I recommend this one, definitely. And now we're going to do our diagonals. Those are going to be the positive ones. For the j, we get a 0. And for the k, we get a 2. So let's write, actually, let's just grab each one of them and let's write the resulting vector. So I have enough room here, actually. So let's go ahead and do for the I, what do I have? I have the 2t times 60, I get 12t squared. I was too optimistic with the space here. Minus, unless I get a 0, but I didn't. Minus 6t squared on the opposite direction. Minus 6t squared. So since I gave myself so little room, it's because I knew they would cancel, and I'm just going to get 6t squared. 12 minus 6 is going to be 6. No, that wasn't planned. All right, but let's take a look at the j. For j, I get 0 in this direction, and on the way back, I get minus 60. So minus 60 j. And for the k, in this direction, I get a 2, and in this direction, I get a 0. Different color. So here I get a 0, because it's 0 times 2t. It goes away. In this direction, I get a 2. So I'm going to have plus 2. Oops, wrong color again. Plus 2k. All right, and I need the magnitude for this vector. Now, I already computed derivatives and all that. So now is the time to evaluate at your point. Because once you took your derivatives, you're safe. You can evaluate, and then you're going to compute magnitudes of numbers. So at 1, 1, 1, r prime cross r double prime just becomes the vector 6, negative 6, and then 2. And r prime, I should use a parenthesis at 1, 1, 1, I suppose. Or at t equals 1 would be my my value here. So let's put at 1. It's just evaluating r prime at 1, which is 1, 2, 3. As easy as 1, 2, 3. And then all you have to do for your curvature, which I have almost no room, is compute the magnitude of this divided by the magnitude of this. And so I'm going to write it here. Kappa is going to be, the magnitude of this is going to be the square root of the sum of the squares. By the way, the magnitude of this one I said, but cubed. Did I do the 3/2 when I wrote the formula here? No, I forgot my cube. Fail. So this would be to the power of 3/2. It's going to be the square root of the sum of the squares, which is going to be 36 plus 36, 72, plus 4 is going to be 76 over, now this one was to the 3/2, that's where I didn't do it well. 1 square plus 2 square is going to be right now 5, plus 3 square 14, so 14 to the 3/2. And then you would simplify that, and that would give you your curvature. Of course, if you don't like that, you could also try to compute your curvature using this formula right here. And that one you will find that it's a lot messier because you're going to end up with, as I said, a quotient rule here. And I really, if you're doing it in 3D, I really recommend this formula. I think it's the easiest version, way to compute it. And if you're in 2 dimensions, if it can be written as a function of x, you use this one. And if it cannot be done, you go back to the first one we computed. All right, sorry about that cube. I'm going to have to put a little note. So you already saw the note because I put it when I edited the video. So thank you for watching, and I'll see you in the next one.